We can imagine a reaction mechanism that might look something like this. We've got A and B reacting to form an intermediate. We call it X. And we've got a first step and a backward first step. We can imagine a situation where those are relatively fast, and then a second step where we could form our product. And we could imagine that this might be slow. Now this, of course, is not always the case, but in many cases it will be true. We can imagine something, imagine that we're protonating something. Well, protonation, deprotonation is usually very rapid. So if we have an acid catalyst, we can have a step like this, and then our protonated reactant can go on to form a product, and that could be relatively slow. So if we were to punch in numbers that correspond to a rapid pre-equilibrium into a spreadsheet to do a numerical analysis of this, we'd see that we've got a relatively rapid forward reaction rate constant. We have got a relatively rapid backward rate constant, but then the rate constants for the forward and backward on the second step are relatively slow. So what happens? We use up our reactants, we produce an intermediate, and notice that the ratio between them is constant, right? It looks like about a 2 to 1. And they both slowly decrease, but the ratio between them stays the same. So we can say that they're in a sort of quasi-equilibrium. And then we're forming a little bit of product very slowly. And so as we drain off product, this equilibrium constantly reestablishes itself. So with that in mind, let's analyze this. Remember, we said that this is going to be a quasi-equilibrium because we drain off the intermediate so slowly that even as we pull off little molecules from here, this is going to reestablish itself as an equilibrium. So then we can say K equilibrium for the first step is going to be the concentration of X over the concentration of A times B. And remember, so during the course of the reaction, these are in constant quasi-equilibrium. Okay, and we could also say for any equilibrium, for any single step equilibrium like that, that the equilibrium constant is going to be the forward rate constant divided by the backward rate constant. So we can solve for X. We can say X is going to be K1 over K1 prime times the concentration of A times the concentration of B. All right, now that's convenient because if we want to know what's the observed rate law for this mechanism, we could say, well, what if you monitor the production of P? We could say dP dt. We call that the speed of the reaction. It's going to be just K2. And then we look at this and say, oh, it's unimolecular in X, so it's just going to be the concentration of X. But we have an expression for the concentration of X over here. So we can just put that in there, and we get V is equal to K2 times K1 over K1 prime times the concentration of A times the concentration of B. And if we were to do experimental kinetics, we would just note that it's first order A, first order B. We don't actually know that it's composed of this. So what's observable is just that it is a overall second order reaction. So this is what we would measure experimentally. The experimental rate law is here. The theoretical rate law is here. And so notice if you somehow knew these individual mechanistic rate constants, we could combine them and calculate the experimentally determined rate constant K observed.